So today I will speak about the optimality results.
Maryina, sorry, that hasn't come up yet. It's there we go. Yeah.
So today I will speak about the optimality results Martin has already mentioned, and maybe it was a bit. So I also will try to explain why these optimality results are possible and why are they possible in dimensions 8 and 24. Because as we will see that something unusual is supposed to happen in this dimension, certain number theoretical coincidences should occur so that our methods work and give sharp results. And so first, let me introduce the two main characters of my talk today, main heroes. So the first here is the E8 lattice. We will denote it by lambda 8. So it's a lattice which is embedded, to think of it as a lattice embedded into a standard Euclidean space R8. So this is a standard Euclidean space with a standard Euclidean norm. And so therefore this norm can be also pulled back to our lattice. And so E8 lattice, it is the unique even and unimodular lattice in this particular Euclidean space, of course, up to an isomorphism. And so what does it mean for a lattice to be even? It means that if we take any vector in the lattice and compute its length squared, then we will get an even integer. And unimodular, it means that the co-volume of this lattice is 1. And so such objects, they are relatively rare. So such lattices, which are both even and unimodular, they can exist only in dimension divisible by 8. And it was known first from the mass formula that such a lattice should exist, at least one such lattice should exist in dimension 8. And so this was proven back in 19th century. And then the concrete the construction was made by Russian mathematicians Zolotarov and Kokorin. And so now this lattice E8, it appears in many areas of mathematics. So for example, so it's probably most famous for being the root lattice of the E8 root system. So it comes up in the classification of simple Lie groups. And also this lattice, it has a number of optimality properties. So for example, the shortest vector in E8 lattice, it has length square root of 2. And there are exactly 240 such vectors. And so these vectors, they form a kissing configuration in dimension 8. And this is a kissing configuration with maximum possible number of spheres. So what is a kissing configuration? So the problem we are considering is the following one. So we are fixing one unit sphere, say, call it a red sphere. And now we consider a bunch of blue spheres. So, and the condition for these spheres is that they are not supposed to intersect with each other. And also each of these blue spheres is supposed to touch our red one. And so the question is, what is the maximum possible number of such blue spheres? So for example, in dimension 8, we can have 6 of them, and it's more or less clear that we cannot fit more. And in dimension 3, the solution is we can have 12 spheres touching one central one. And this is a famous Newton-Gregory dispute, so which was resolved only in 19th century. And in dimension 4, this kissing problem was solved, I think, 10 or 15 years ago by Oleg Musin, and it was a very, it was a big breakthrough. So like these kissing problems are difficult, and they already become extremely difficult even in dimension 4. And in dimension 8, we know that we have these 240 balls. And so this configuration, it is so good that this kissing problem, it was solved much earlier than the problem for dimension 4. And so as we see, not only that this number 240, it's a very big kissing number for dimension 8, but also the method which proves optimality, it works in very rare occasions. So it works for dimension 8, and in the next slide, we will see another occasion when same method works. And finally, when we have our E8 lattice, we know that the shortest vector in this lattice has length square root of 2. So what we can do, we can put a ball of radius 1 divided by square root of 2 into each point of the lattice. And this way we will obtain a sphere packing, a configuration of non-intersecting open unit balls in dimension 8. And it turns out that this configuration, it is the densest possible in dimension 8. And so this is the result I'm going to speak about today and give you some insights about the method of the proof. And also E8 lattice has another remarkable property. It is that it is universally optimal. So it's optimal not only for sphere packing, but it's optimal for a wide range of energy minimization problems. So if we think of our points, for example, as electrons which repel each other with a certain law, which we somehow, we can actually change. And then, for example, we confine our electrons in some very big box, so they have so to say fixed density. Then these electrons will arrange themselves into an E8 lattice. And so this is a theorem which we've proven together with Henry Kohn, Abhinav Kumar, Steven Miller, and Danilo Radchenko. And so another remarkable object I'm going to speak today is the Lich lattice. So the Lich lattice, it's a lattice in dimension 24. And in dimension 24, there exists 24 even and unimodular lattices up to an isomorphism. And so among those 24 lattices, we have only one such that its shortest vector has length 2. So for even, because the lattice is even, it means that the shortest vector can be square root of 2 as it was for E8 lattice. And this is the case for 23 of these lattices. But there is one among 24 such that the first possible length does not occur and the shortest vector has length 2. So the Lich lattice was discovered already in the 60s by a Lich who it is named after. And there is many different constructions of Lich lattice. Basically, it seems like if you try to construct a lattice in dimension 24 and you have a clever idea, then most likely you will end up with Lich lattice. And so in a famous book of Conway and Sloan, I think there are at least 10 different constructions, and new constructions keep occurring. So it can be constructed. So there are constructions, for example, given by error correcting codes. These are the constructions we're going to discuss later today. It can be constructed from cyclotomic fields. It can be constructed from elliptic curves. And there are many ways to construct the Lich lattice. And so now for the Lich lattice, we know that its shortest vector has length 2. And so this time we have this 6-digit number of shortest vectors. And we also know that this number is maximal possible. And so this is exactly the kissing number in dimension 24. And this result was proven the same year as the corresponding result for dimension 8. And it was also proven by exactly the same method, which we will speak about later. And so now also when we have a Lich lattice, from this lattice, what we can do, we can we can construct a sphere packing. So now we are putting one ball of radius 1 with center at each point of our Lich lattice. So this way we will get a sphere packing because these balls, they will not intersect. And so the so this packing, it turns out to be the densest possible packing in dimension 24. And so this is the result we have proven together with Henry Kohn, Abhinav Kumar, Stephen Miller, and Danilo Radchenko in 2016. And also, we have shown that similarly to E8, the Lich lattice, it is also universally optimal. So if we think of points of our E8 lattice as equivalent particles which repel with a certain potential of a nice shape, and what does it mean for potential to be nice? I will explain it later. So then the points will arrange themselves into a Lich lattice. And so now to explain how we were able to prove these results, let me introduce maybe more general packing problem, not only in Euclidean space. So in principle, we can work with any metric space. So we have our metric space mu, and rho would be a metric on it. And then for any metric space, we can define what is a ball. It's a clear, so ball is just, well, centered at some point. It will be just the set of all points of our metric space, which are at distance at most r0 from the center. So this would be a ball with, if this is point x, and this would be the ball with center x and radius r0. So this definition works nicely in any metric space. And so the general question we can ask, how many balls of given radius can be contained in this metric space? And about how many, so this, for example, if our metric space is compact, then how many means just exact number. And if our space is not compact, and if it can contain infinitely many balls, then we should speak about some kind of a density of our balls, or density of the centers of balls in our metric space. And so this problem also has another version. So we say that subset X of M, it is an R code if distance between any two distinct points of X is at least R. And so the problem of finding good R code is almost equivalent to the problem of taking balls of radius R divided by 2. And so here are some famous problems which fit into this definition, this framework. So first, it's a sphere packing in Euclidean space. So in general, it fits into this formalism. Only we have to clarify about how many, what explicitly that means. Then another very famous application is the construction of error correcting codes. And so it works like this. So our space M, it will be the space of sequences of symbols in a certain alphabet. For example, here, this is a sequence of zeros and ones. And whenever we have two such sequences, we can define a Hamming distance between these two sequences. So we are searching for all positions where our sequences have different elements, where elements of, sorry, here it actually does, sorry, no. Where the elements of these two sequences do not coincide. And then the number of such places, we call them the Hamming distance between these two sequences. So in this case, the Hamming distance between these two sequences would be 2. So another well-studied problem is the independence number of a graph. So if we have a graph, we can think of a distance between two vertices as the length of a shortest path between 2 points. And then we want to find maximal possible set with maximum possible number of vertices such that no two elements in this set can be connected by an edge, so that no two elements are at distance 1. And so this problem is also very well studied in discrete math. And the problem of finding good packings or good codes, it can be generalized or so to say smoothened in the following way. So very close problem, which is very close to it, and many similar methods apply for its analysis. It's the problem of minimizing potential energy. So here we fix again our metric space, and now we consider some finite subset in a metric space, and we define our energy profile. So it will be any function from the support of our metric row, for example, into real numbers. And then we say that the potential P energy of this finite set C, it would be such a sum of all pairwise interactions between 2 points in our metric space, where we think that the strength of the interaction depends only on the distance between them. And also it will be convenient for us to normalize this energy so that divide by the total number of points in set C. So this becomes like an average energy per one point in the metric space. And so there is one problem with the questions I've described to you now. So they seem to be somehow non-linear and rather complicated. And so the one idea of trying to analyze this kind of problems, the packing problems and energy minimization problems, is to linearize them, to reduce them by a suitable problem, for example, in conic optimization. And then in conic optimization, there is it's a very nice suited for solving inequalities. Here we have many nice results, many nice algorithms. Here we have a notion of duality. And so this duality can help us proving effective estimates. So here I just remind you that what is a cone? Cone, it's a positive cone, it's a subset on, for example, in Euclidean space, or it can be in other, it can also work if the space is not necessarily finite dimensional. And so the condition is that if we have two elements in our cone, then their convex linear combination also has to belong to our cone. And so here's one example. This is a so-called ice cream cone. So a simple one. And so a nice property of conic optimization is that here we have a well-defined and very nicely working concept of duality. So whenever we have some cone C, we can always define its dual cone. And then whenever we're trying to solve a linear an optimization problem on this direct cone C, for it we can always construct a dual program on which is somehow related to the dual cone. And so here what is nice, the relation between these two problems, it is that any feasible solution to one of these problems, it gives us an estimate for the second problem. And so instead of having one optimization problem, now we have two of them. And we know that finding any feasible solution for one of the problems, it gives us the bound for the solution for the second problem. And so here's the way, like what's the con which we should consider if we want to analyze packing problems or energy minimization problems on metric spaces. So here there is a nice con, so there should be a con of functions on this metric space. And then one nice con is the con of copositive functions. And it is defined in the following way. So let M rho be a metric space. And so we consider it's suppose that it has some support. So the rho has certain values. And then we say that a function f from the support of rho to the complex numbers, it is copositive if the following sum is always non-negative. And this is true for all finite subsets of M. And now you can see that, for example, checking whether certain energy is minimal for a metric space, it is essentially becomes the problem of solving a question whether certain elements belongs to this the cone of copositive functions. So if we were able to describe this cone easily, then we could solve all the problems I just I spoke about before. But here the problem is that for interesting metric spaces, this cone is usually very difficult. And so solving all the problems related to it, for example, checking whether a certain element belongs to this cone or not, it's usually a computational, very difficult problem. As well, now, both computationally and also, so say, if you're interested in pure math, also theoretically. And so we have, for this reason, we can consider different cone of functions, which is a subset of the cone of copositive functions, so-called positive definite functions. So this is also a function from the support of our metric to the complex numbers. But here we are posing stricter conditions on our function f. So here we don't require not only that all such a double sums are non-negative, but there should be all double sums like this with all possible weights. So here for our finite set x, for each of the points in x, we are assigning certain weight wx, which is a complex number. And then such a weighted double sum should be always non-negative. And if this holds, then we say that our function f is positive definite. And so it's obvious that positive definite functions, they are subset of all copositive functions. And so typical situation looks like this. So this cone of copositive functions, it's a complicated object and we cannot work with it directly. Usually proving that the function is copositive, it is very difficult. At the same time, for many metric spaces, especially if there is a big group acting on our metric space, then this cone of positive definite functions, it is, so to say, simple. And often this cone, it can be described in terms of the harmonic analysis happening on this metric space M. And so as I say, this works particularly nice if M has some additional structure, for example, like an action of a big group. And so now our main tool for proving results on sphere packing would be the following theorem. So suppose that we were able to construct a copositive function, or copositive here, I can also replace it by, so in reality, what we will often do, we will not construct a copositive, but we will construct actually a positive definite function. Function f, such that its value at 0 is 1, and it's smaller or equal than -1 divided by n minus 1 for all values of r which are bigger or equal than r0. And if such a function exists, then we know then that R0 code in this metric space, it can contain at most capital N points. And the proof is very simple. It's so we simply have to write this double sum and estimate it from above and from below. So first we estimate it from below just by using the fact that F has to be positive definite. And then we estimate it from above by using these two conditions and the fact that we assume that X was an R0 code. And so now by comparing these two estimates, we see that the R0 code can contain at most capital N points. And so now this very simple principle, it's actually our blueprint for the proof of all the optimality results mentioned before. And so now somehow what the trick becomes to find suitable function F. So this becomes a difficult part. And so let me first show you a few compact cases when this principle works. So as I already told you that this principle, it works for the sphere kissing problem in dimensions 8 and 24. And so this is how Levenstein and Lischko and Sloan, this is exactly how they solve the problem. They simply find this suitable function F. And in this case on a sphere, because sphere is a metric space where the big group is acting, namely the orthogonal group. And so the cone of positive definite functions has an easy description. And so they simply compute the suitable function and prove the optimality result. And in their case, this optimality function, it is a polynomial of a rather small degree. And here is another similar situation. So this is a situation of a Hamming code. And Hamming code, it is a subspace of dimension 4 inside of a vector space of dimension 8 over the finite field with two elements. And so this matrix, it's a generator matrix for the code. So we have to consider these vectors and all their linear combinations. And then we will obtain all elements of the Hamming code. And the minimal distance of Hamming code is 4. And it contains 16 elements. And so now what we are going to see, we are going to prove that these numbers are optimal. And so, well, the question is, how can we construct some positive or positive definite functions on this metric space? And so here's one idea. So first we will see that such harmonic waves, even though they are not elements of somehow they depend not only on the distance between 2 points, but rather on a scalar product. But at least like these functions, they would satisfy this condition of positive definiteness. And so now if you want this function to depend only on a distance between 2 points, what we are doing, we are taking the averaging. So we take this function and then we average it, for example, over all points at a given distance. And then what we obtain, then we will obtain the so-called Kravchuk polynomials. And these Kravchuk polynomials, they are positive definite functions on this metric space. And so this is the well-known result that if we have a code of distance 4 inside of this 8-dimensional vector space, then it can contain at most 16 points. And we do this by constructing a suitable function. And this suitable function, it is the following polynomial. And this polynomial, it can be expanded as a linear combination of Kravchuk polynomials. This is because Kravchuk polynomials, they are orthogonal polynomials and they form a basis of the space of all polynomials. And so how is this polynomial constructed? It is constructed in such a way that like all the distances inside of the Hamming code between any two elements of Hamming code, they can be either 0 or 4 or 8. These are all distances. In the Hamming code. And so we are constructing a polynomial which vanishes at all of these distances except for the 0, 1. And now it turns out that this polynomial, it has all positive coefficients when it is expanded as a linear combination of Kravchuk polynomials. And so this means that this function f, it will satisfy the condition, and it's also somehow now the value of the free term in this formula. It gives exactly the value which we need to prove the optimality. And so the optimality of Hamming code is proven by linear programming. And so now when we start with the Hamming code, one of the ways to construct E8 lattice is to construct it from Hamming code. And so here is the construction, which in the book of Conway and Sloan called construction A. And it works for any binary code. It tells us that suppose that we have a binary code of dimension n and distance d, then we can consider the following lattice. So this is the lattice which consists of all elements in this code plus 2 times the lattice Zn. And then it's easy to see that this will be a periodic subset in Euclidean space. And then if our code, if it was a linear code, then this periodic subset, it will be a lattice. And if we know parameters of this binary code, then we will be able to compute the density of points in our periodic set lambda c. And we can also estimate its minimal distance. And its minimal distance, it will be bounded from above by minimal distance squared. It will be bounded from above by the distance of the code and by number 4. And so if we apply this construction to the Hamming code and then rescale it so that the resulting lattice is unimodular, we will obtain the Lich lattice E8. And so the optimality of Hamming code was proven, can be proven by linear programming, which is actually, it's rather unusual. There are not so many configurations for which this method works. So usually it gives just an upper bound, or rather lower upper bound for the density. But in general, we don't expect a sharp solution. And so this happens here in this finite dimension, this finite situation. And we will see that the same happens for E8 for in the Euclidean case. And so the Lich lattice, it has similar genesis. And so one of the many constructions of Lich lattice, it's also the one starting with binary codes. So here one can take a binary Galais code. So this time it's a code of dimension, of length 24. And it's a vector subspace of dimension 12. And its minimal distance is 8. And so the Galais code, it's also an optimal code. And its optimality, again, can be proven by linear programming. So here again, we have this suitable polynomial, which is constructed just from knowing the possible, or the set of all possible distances in the Galais code. And if we expand these polynomials as a sum of Kravchuk polynomials, we again get all the non-negative coefficients. And so we can apply our theorem. And so now constructing the Lich lattice from the Galilei code is not that simple. So here we have to use what is called in the book the construction B, and it's slightly different from construction A. And so here what happens after we apply this construction B, we can actually fit two different copies of this periodic set into Euclidean space. And these two copies, they will differ by a translation. And so this will give us the Lich lattice in dimension 24. And so the theorem which I've shown you on the previous slides and which shows the optimality of the Hamming code and Galilei code, it works nicely for compact metric spaces, but it would not work for the Euclidean space. And so Kohn and Elkis in 2003, they have adapted this linear programming method to Euclidean space. And so they've proven the following results. So suppose that we are able to construct a function f such that f satisfies the following rather similar but still a bit different conditions, so that f of x is smaller or equal than 0 for all values of x where the norm of x is bigger or equal than R0. Suppose that the Fourier transform of f is non-negative and our function is normalized so that its value is 0 equals to the value of its Fourier transform at 0 equals to 1. Then we say that each periodic configuration such that the distance between any 2 points is at most R0, it has a point density at most 1. So it means that any R0 code in Euclidean space would have density at most 1. And so Kohn and Elkis, they have applied this method numerically to many dimensions. And so this is somehow this blue line, these are the known densities of actual configurations, and they are believed to be optimal, at least maybe up to, I don't know, maybe up to here. And so this red line, it is the bound by Kohn and Elkis. And so you can see in this plot that for dimension 8 and dimension 24, the bound is almost sharp. And so Kohn and Elkis, they have proven numerically that if there is a, so here delta D, it is the sphere packing constant. Which is the density of the densest sphere packing. And so they've proven that even if there is some improvement in dimensions 8 and dimensions 24 comparing to the E8 lattice and Lich lattice, this improvement is truly small. And so what I was able to prove is that there exists a radial Schwarz function FE8, which satisfies somehow the best possible constraints of the Kohn-Elkis theorem. And so this function, then it gives the sharp bound. And also together with Henry, Abhinav, Steven, and Danilo, we have proven the similar result for dimension 24. So what we have done, we have shown that there exists this function in dimension 24, which also satisfies all the optimal constraints for dimension 24. And so these two functions, they prove sharp bounds for sphere packing, and therefore we call them the magic functions. And so how much time do I still have?
Well, it depends how much time we want for questions, but I would say another 5 minutes is okay.
Okay, good. Thank you.
Probably not more, but 5 is okay.
So here is the plot of this magic function for dimension 8. And so the plot for its Fourier transform. And so what can we see? This plot is that these functions, they also vanish a lot. Both functions, they vanish up to second order at the all possible lenses, all lenses which appear in our lattice E8. So, okay, so here I'm plotting this lens square just to make my plot look a bit nicer. So we know that every vector in E8 lattice, its length, it will be a square root of an even number. And so this function also vanishes at all square roots of even numbers. And it turns out that this information is actually sufficient to find both functions f(E8) and f lambda 24. So both magic functions, they can be found just from knowing this vanishing. And this is actually very similar to the situation we had for the binary codes and the situation we had for kissing numbers, that we know this set of possible distances, and set of possible distances guides us and gives us the magic function which solves our optimization problem. And so here, without loss of generality, we may assume that our both functions, they are radial functions. So as you can see on this plot, it's not a function of 8 dimensions, it's only a function of 1 dimension, which is the length of the vector in 8-dimensional space. And so also, for example, from the Poisson summation formula, we can see that our function, if it satisfies all the constraints of Kohn-Elkes theorem, then its values at all non-zero vectors of our lattice, they are supposed to vanish. And because of the Kohn-Elkes constraints, this vanishing has to happen up to the second order. And so now this information, it is sufficient to find these two functions explicitly. And so here's the method which works. So this is the chicken claw contour integration. So if you know, so this is a hut which stands on a chicken claw, and this is exactly the contour we are going to integrate over. So we are searching for our function in this form. So we know that our function, it vanishes up to second order at all these points. So how can we stimulate this vanishing? So we are just multiplying by sine squared. But this, if you take just this function, it does not work. Its Fourier transform will not be a nice function. It will not solve our problem. So we assume that we have to multiply this function by something non-negative, or something which is actually, it's non-negative if r is bigger than the smallest root of our equation, and then it also changes sign. Something what will change sign for us. And so, so here in this situation, so here this function phi, it's a holomorphic function, which is defined everywhere on the upper half plane. And we also assume that our holomorphic function has nice transformation properties with respect to the action of the group SL to Z on the upper half plane. So group SL to Z, it's the group of 2 by 2 matrices with integer coefficients, and this group acts on the upper half plane by linear fractional transformations. And so here, how do we know what is a nice transformation? So this I can show you. So we are writing our function f of r. We assume this integral representation. So here we are writing sign in a slightly different way. So at this step, we are moving this exponential factors, grouping it together with the Gaussian, with this complex Gaussian here. And now instead of integrating over one contour, over this one, we have three different integrals over these three different lines. And now what we are going to do next, now we are applying the Fourier transform. So now let's forget about convergence issues, just apply Fourier transform to this function. So then for the Fourier transform, we assume that it commutes with these contour integrals, which of course we have to justify. But if you believe that I've done that homework, then we only have to compute the Fourier transform of the Gaussian. And this is where the action of the group SL2Z is coming up, is because the action of Fourier transform on Gaussians is very similar to the action of a particular element of SL2Z on the upper half plane. And so in the next slide, so now we continue working with these contour integrals. So here what we do, so this is where the chicken claw is coming into. So we wrote this integral like this. And now instead of these three integrals from vertical lines, we are replacing our integral by a chicken claw like this. And so now we are rewriting this integral again. And so now what we want to achieve now, so we started from, we wrote our function f in this special form because it's easy to read zeros from this special form. And now what we want to achieve after we have done the Fourier transform, we want our Fourier transform to have the same shape. But now it does not look like it has the same shape because all the functions in these different integrals, they look quite different. And so what we can do, so let's just search for function phi, which satisfies the special transformations with respect to the modular group, so that the Fourier transform has same shape again. And so we can write all these functional equations. And what it turns out is that maybe what's somehow a big, well, or maybe not a big, but at least a surprise here is that these equations, they can be solved explicitly. So. And this is where the theory of modular forms comes in. So it gives us a very explicit formula for a function phi, which would satisfy all these conditions and also which would be holomorphic at the upper half plane and will have right behavior at infinity so that all our integral manipulations are indeed justified. And so when we have found this reasonable function phi, we come up with this solution. So now we see that the Fourier transform again has double zeros. And this is what we were searching for. And then probably at this point, I will stop and then answer the questions.